All right, here comes section 8.6. This is the last one for Unit 8A. And then we've got a few more sections to go for Unit 8B. But we're almost there. We are almost there. This one's talking about finding the area between curves when there's more than one point of intersection, or more than 2 points, I should say more than 2 points of intersection. So I see this picture here, and you can see that they've got a point of intersection down here. They've got another point of intersection here, and they've got one here. So you've got 3 points of intersection with this. And the deal is, if I think about my representative rectangles that I've talked about, let me draw one in this shaded area. Right, here's my representative rectangle. Here's another one over here in this shaded area. And if I look at that one, check out the functions on top and bottom. On this case, if I look at this one, the cubic function is the one on top, and the parabola is the one on the bottom. Where in this case, the parabola is on top and the cubic's on the bottom. So it switches. Where does it switch? Switches right here at this coordinate. So we need to come up with, what are these points of intersection? That's going to be my first thing. And then I've got to divide my integrals into 2 separate parts, because what's on top and what's on the bottom changes. So job number 1, let's figure out these points of intersection. If I take to figure that out, I'm going to set the 2 functions equal to one another. This one's not so bad. 3x cubed minus x squared. Sometimes we'll use a calculator, but this one's pretty. All right, equals, and then I've got a negative x squared plus 2x. My job is to solve for x. So I'm going to get everybody on the same side of the equal sign. That's going to give me a 3x cubed. And when I bring this negative x squared over, it turns into a positive x squared, joins up with this guy, they knock each other out, and we don't have an x squared. But I do have a 2x that comes over and joins with the 10, they become negative 12x. So I'm going to factor that. Out comes a 3x, leaves me with x squared minus 4. I set them equal to 0, and I get x equals 0, and x equals, think about this, plus or minus 2. So my first value, A, this is B, this is C. My first value is negative 2, then I go to 0, and then I go to positive 2. That would be the order that I go in. So you just figured out the points of intersection. Let's set up the integral that represents the total area. All right, well, the first area goes from A to B. In this case, these are nice numbers, so I'm just going to use the numbers, but you'll see in a little bit that I might just use the letters. Once I've identified what A, B, and C are, I can just use those letters in my integral. But for now, they're easy numbers, so we're going to keep it that way. The first one goes between negative 2 and 0. Who's on top? The cubic. That would be 3x cubed minus x squared minus 10x. And on the bottom is my parabola, negative x squared plus 2x. All right, there's the first area, top minus bottom. Go into the second area. Now this one goes from 0 to 2. So I have an integral from 0 to 2. And this time my parabola is on top, negative x squared plus 2x. And on the bottom is my cubic, 3x cubed minus x squared minus 10x dx. And that's it. That's all you have to do. Now, interestingly enough, you can also use, and I don't normally do this, normally I just kind of break it up the way you're supposed to break it up. Also, I could simplify this better. I could combine like terms. But, you know, sometimes the more work you do, the more area for mistakes. So simplifying is not necessary for these. It might be if you want to put it in a calculator, if you were asked to actually solve it out. It might be nice to simplify it a little bit more so that you don't have to put as much stuff into your calculator. But that's a perfectly valid answer that you've got right there. Now you can also use absolute value and get the same answer if it's a calculator active question. So if you can use a calc, here's another way you could do this. You could literally go from A to C. You can go from negative 2 to positive 2 and take the absolute value of f of x minus g of x with respect to x. Now realize that is not taking the absolute value of the integral of f of x minus g of x. It's not that. They're not the same things. So this can kind of, if you're not remembering that, this can kind of get you into trouble. I usually, like I said, go back and do this style when I'm doing them, just for safety matters. All right, here comes the last example problem before we get into practice problems. So the figure shows unhappy parabola and a line y equals 1 going between x's of -2 and 2. Set up the integrals for the sum of the areas of the shaded region. Well, how many areas do you have? You actually have 3, right? You've got this one here that goes from 0 to whatever this coordinate is. And then you've got this one here. I'm putting in my representative rectangles for each one that goes from here to here, this point of intersection. And then my last one is this point of intersection with a representative rectangle over here. But my job is, I need to figure out what these, I can see what this is. I can see those coordinates pretty easily. But I have no idea what these coordinates over here are. And the way I'm going to get them is to set the two functions equal to one another. Again, this one's not so bad. We're going to sometimes use a calculator to do this, but this one's still okay. I take my unhappy parabola and I set it equal to the line y equals 1. And then I solve it out. So -1/2 x squared equals, bring the 2 over, -1. Negatives cancel. I multiply both sides by 2. That gives me x squared on the left. X squared. Gives me 2 on the right. So x equals plus or minus the square root of 2. That's what these two are. All right, so they want me to set this up. I have 3 different areas. I'm going to have 3 different integrals. The first integral goes from -2. This guy here would be a negative square root of 2. This will be your positive square root of 2. And then you got the last one over there at 2. So first one goes from -2 to negative square root of 2 over 2. I'm sorry, just negative square root of 2. Where's the top? The top is 1. Hits that line at 1. 1 minus. Where's the bottom? The bottom's the parabola. 2 minus 1/2 x squared. There you go. There's the first one. Second one goes from negative square root of 2 over 2 to positive square root of 2 over 2. Why am I doing that? I'm thinking, I just did it. I was just doing a video with sines and cosines. So maybe that's what I'm thinking of. It's just a square root of 2. Negative square root of 2 to positive square root of 2 over. Oh my goodness. Get the trigonometry out of my brain. All right, this time I have the parabola on top, so he is a 2 minus 1/2 x squared. The bottom hits 1, minus 1. And then I have the last one, and it goes from the square root of 2 to 2. Square root of 2 to 2. Top is hitting 1. Bottom's hitting the parabola. And again, I could simplify this out, distribute the negative, and simplify each grouping. And again, I wouldn't recommend doing that unless you have to put it in a calculator. Mr. AP is okay with it being left unsimplified. All right, that is it for the notes. And I have just a couple problems that I want to work with you. The first one is number 2. Number 2. You have this wonky function, x plus e to the x squared minus 3x, and you've got another one that's a parabola, 2x squared minus 4x plus 2. Now, I had the hardest time drawing this when I was trying to do this on the calculator, because I went to the calculator for this one particularly. This is a calculator question. They don't really tell you calculator or not calculator, but like numbers 1 and 3, they're perfectly easy to, when you set the two things equal to one another, they come out pretty. You don't really need a calculator for number 1 or for number 3. But number 2, how would you know? Like, who knows what the e's are, right? This one you definitely need a calculator to do. So let me give you a try. I'll try really hard to give you what a picture looks like of this guy. You've got this really weird e to the x function. It comes down. Actually goes kind of wide. Comes down, curves here, kind of goes flat, and then goes up again. And then you have a parabola, and the parabola comes down Oh, this is going to be hard for me. Comes down, it goes through here, it comes back up here, and it goes through like this. Did I get 4 points of intersection? I did not. Like I said, this was not pretty for me to try to graph. My issue is over here. Maybe I'll just show you this. This was what I got when I graphed it. Okay, you end up with this wonky looking thing. And what I did was I put them in my calculator, and then I changed my window so I could kind of zoom in on what's going on. So I'm going to use this picture right here to explain the rest of this, since my picture I was trying to draw didn't work. All right, so I go to the calculator, and I literally had to calculate what these 4 points of intersection are. So I go to the calculator, and I went into the math menu after I graphed it, and I figured out what each of these values were. Here you got negative 0.4407. You've got 0.3872903. That's this guy. Then you've got 2.0459255, and then you've got the last one at 3.6407356. And then really the only reason I graphed it and was really pretty adamant about that is because I need to know what functions on top and which functions on the bottom to be able to set all these up, right? I have 3 different areas that I need to add up with my representative rectangle in each one so I can tell who's on top and who's on the bottom. So points of intersection. Again, if you don't know how to do this, if you can't find the points of intersection on your calculator, let me know and I'll help you in class and show you how that works. Now, you're using some crazy decimal points, right? I went out like 7 places in some of these. So you want to take as many decimal values as you can. You don't want to round to the end. And I called this one A, this one B, this one C, this one D. So that when I set up my integrals, all I need to do, if I've identified them somewhere, is just use the letters. Ain't nobody want to write all that out, right? It's not like those first couple examples we did when they were like -2, 0, and 2, which were perfectly just as easy to put those numbers versus the A, B, and C. Okay, so first one goes from -0.4407 from A to B, and in this case the parabola is on top and the E function's on the bottom. There you go. Next one goes from C to D, from B to C. That one has the E function on top and the parabola on the bottom. That's this guy. Last one goes from C to D. Again, you've identified what C is, you've identified what D is, so you're allowed to do this. And on top is your parabola, and on the bottom is the E function. And so there it is, you've set it up. So this one's a little different than some of the example problems because this one you need the calculator to figure out what your points of intersection are. All right, there's number 2. Last one I want to do is number 6. And again, this one's a little tad different than some of the other ones. It shows the figure of the absolute value of x and a parabola that have joined up here. The x coordinates of the points of intersection on the graph are x1 and x2. He's saying this. We're going to call this one x1. In other words, you don't have to find it. You're just going to use the notation x1. This one has a notation of x2. You don't have to solve for x1 and x2. Write the sum of integrals that represents the shaded region. So again, I'm all about those representative rectangles, right? First shaded region is over here. Kind of hard to see that, but here's my representative rectangle in the middle. And then I have one at the end here. Well, the first area goes from -1 to x1, whatever that x1 is. So the first one is from -1 to x1. What's on top? The absolute value. And on the bottom, therefore, is my parabola. 3 minus or plus 2x minus x squared dx. There's my first shaded region, this guy. Then the next one goes from x1 all the way to x2. Because that entire region has the top being the parabola and the bottom being the absolute value. So I can put it all together that I'm going from x1 to x2. Top is the parabola. 3 plus 2x minus x squared. Bottom is my absolute value of x. And then the last one is going from x2 to 3. Let me do my integral sign first, right? And my integral goes from x2 to 3. And on top now is my absolute value. And my bottom is the parabola. Write a sum of integrals that represents the shaded regions. There you go, you did it. The only thing that was a little crazy about that one is that you're using x1 and x2 rather than actually finding those points of intersection. So it kind of was relatively easy, but it just, I didn't want you to get confused by the wording of that one. And the last piece I want to tell you is that in number 7, there's a typo, that this should be y equals 3. If I look at where the two lines are, there's a line at y equals 1. Sure there is. But the second line's at y equals 3, not y equals 2. This should be a y equals 3. And then you can answer out that question. All right, that does it for the beginning of Unit 8. And we are going to finish up Unit 8, and then we are done ski for the year ski. So I will see you in class. Shoot me an email if you have questions, or I will see you, like I said, in class to answer anything else. Hang in there. We're almost there. We're almost done.